Hi students, 12th standard chemistry, unit 5 coordination chemistry. We are seeing the examples for valence bond theory. Okay, already we have seen lot of example and this is your book back question. This is the fifth question in your book back. Okay, they are asking to find out the whether this compound is paramagnetic or diamagnetic. Okay, let us find the solution for this problem. So for this, in order to derive this, you have to know the atomic number of the central metal atom. Okay, here the central metal atom here which is nothing but chromium and the ligand is ammonia. The atomic number of central metal atom is 24. Okay, then we have to find out the oxidation state of the central metal atom. Okay, so the complex is Cr NH3 6 3 plus. Okay, so I am going to find out the oxidation state of this chromium. So I am keeping this as X plus how many number of ligands are present here? 6 number of ligands are here. So I am writing 6 and the oxidation number of the ligand. Since this ammonia is a neutral ligand, the oxidation number of this is 0 since it is having a neutral ligand. Okay, then 3 plus I am writing plus 3. So X is equal to, it will be 0. So I will get plus 3. So the value of X is plus 3. So what is the oxidation state of the central metal atom here? The oxidation state of the chromium in this complex is plus 3. Okay. Then the next step, I have to write the electronic configuration for the element. Okay. In order to write the electronic configuration, you should know the atomic number first. Okay. Then only you can able to write the electronic configuration. So the atomic number of chromium is 24. So let me write the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. Okay, so this is the electronic configuration for chromium. Okay, it is our central metal atom. Here we have to take the outer electronic configuration. Okay, 4s2, 3d4 is our outer electronic configuration. I am taking chromium which is in which oxidation state? Plus 3 oxidation state. Chromium is in plus 3 oxidation state. I am taking the outer electronic configuration 4s2, 3d4. Okay, this is the outer electronic configuration. If it is plus 3 means I need to remove 3 electrons from here. Okay, to remove the electrons I am rearranging this 3d4 and 4s2. Why I am writing like this means to remove an electron from s orbital is very easy when compared to the d orbital. So I am writing like this. I have to remove how many electrons? 3 electrons. So I am removing 2 electrons from s orbital and 1 electron from d orbital. So what is the thing I will get here? It will be 3d3. So finally I got 3d3 and 4s0. Okay, this is our outer electronic configuration for chromium plus 3 ion. Okay, so this is our electronic configuration. Then we have to write outer orbital of metal. Okay, for that I have to draw the degeneracy set first. It is d orbital. I am writing 3d orbital. 3d orbital is containing how many electrons? 3 electrons. So I am going to fill the electrons according to the half-half principle. Okay, each set is filled by 1 electron first, then only pairing take place. Okay, but here in this case I am having only 3 electrons. So let me fill the electrons 1, 2, 3. Okay, then the remaining 4s orbital. 4s orbital is 0 and 4p orbital is also 0. So 4s 0 and 4p is also 0. Then the fifth point, nature of the ligand. So we have to see whether the ligand is strong field ligand or weak field ligand. We are having ammonia as a ligand. In some cases, this ammonia will act as a strong field ligand. In some cases, this will be acting as a weak field ligand. But in this case, it is acting as a weak field ligand. Okay. So what is the nature of our ligand? It is weak field ligand. Then I have to write the outer orbital of the central metal atom in the presence of a ligand. Okay. Since it is a weak field ligand, what it will do? There is no pairing is taking place. Okay. Since it is a weak field ligand, the 3D complex will be as it is. Okay. Let me write here. Then 4s, then 4p, it is 3d3 and 4s 0 and 4p also 0. I am writing the electrons as it is. There is no changes and there is no pairing will be taking place. Then I have to write the hybridized orbital. You know what is hybridization already. Okay, we have to mix these atomic orbitals, then we can get the new hybridized orbital. Okay, so I am going to mix these atomic orbital. Before mixing this orbital, you need to see how many ligands are there. 6 ligands are there. Okay, 6 ligands in the sense we need 6 degeneracy set. You just count the empty orbitals 1, 2, 3, 4, 5, 6. So we are having 6 degeneracy set without an electrons. So these orbital will be taking part in hybridization. So let me draw the structure here. This 3d3 orbital I am writing like this, and I am filling the electrons here. 1, 2, 3. The remaining I am going to combine, I am going to mix together to form the hybridized orbital. Okay, 2 orbital from D. Okay, then 1 orbital from S orbital, then 3 orbital from P orbital. I am going to mix all these 3. So 2 from D orbital and 1 from S orbital and 3 from P orbital. Okay, so these 2 from D. Okay, D2 and this from S and these 3 from P. So I am writing D2 S P3. Okay, what the ligand will do? The 6 ligands will donate a pair of electrons to the central metal atom. The ligands will donate a pair of electrons. So I am having 6 ligands. NH3, ammonia will donate a pair of electron to the D1 orbital. Ammonia will donate a pair of electron to the D2 orbital. Then ammonia will donate a pair of electron to the S orbital, and so and so. Okay, it will be written like this. So each ligand will donate a pair of electrons to the central metal atom, to the vacant orbitals, to form the hybridized orbital. So these pair of electrons I am writing like this. So this is the newly synthesized orbital, or this is called hybridized orbital. Okay, then I have to write the coordination number. What is coordination number? Simply we can say, okay, how many ligands are attached with the central metal atom here? 6 ligands are attached with the central metal atom. So the coordination number is 6. What is the hybridization next step? We have already find out the hybridization in the 7th step itself. Okay, what is the hybridization? D2S P3 hybridization. D2S P3 hybridization. So here in this case, the inner d orbital is taking part in the hybridization. Okay, so this is called inner d atomic orbital, inner d atomic orbital. Then we can go for the geometry. Definitely there is a presence of 6 number of ligands. Okay, how many number of ligands? 6 ligands are present. The geometry will be, if it is D2 sp3 or sp3 D2 means what will be the geometry? It is octahedral. We have studied from VSEPR theory. So the geometry of this complex is octahedral. Then we can go for the magnetic property. Magnetic property is in the sense whether this compound contain unpaired electron or paired electron. Okay, see here this complex contain unpaired electron. If the complex contain unpaired electrons means that comes under paramagnetism. So how many unpaired electrons are present? 3 unpaired electrons are there. So this complex exhibit paramagnetism, this compound is said to be paramagnetic in nature. Okay, paramagnetic in nature. Then the last one I have to find, this is our question. Okay, it is the book back question. Already I told you they are telling us to find out the whether this compound is paramagnetic or diamagnetic. We have find out the answer for this. This compound is paramagnetic in nature since it is having the unpaired electron. Then the last one is magnetic moment. What is the formula to find out the magnetic moment? Mu is equal to square root of n into n plus 2, where n is the number of unpaired electron is present. Okay, how many number of unpaired electrons are here? 3. Okay, so the number of unpaired will be 3 into 3 plus 2. You will get the value 4.2 Bohr magneton. Hope it is clear to everyone. Thank you.